So good morning, everybody. So we are going to continue the class. So can somebody pray? Let's start the class with prayer.
Understanding your wisdom made available to us and also help the lecturer explain properly to us in Jesus' name. And the end of glory shall be given unto you in Jesus' name.
Start the class. So I'll start with the assignment. So last week I told you that one of the activities we are going to introduce is paper assignment. So here is a list of um, papers in artificial intelligence. So the first one is attention is all you need. ImageNet classification, Lake Akari, generative adversarial net, BERT, Google Neural Machine Translation, Neural Collaborative Filtering, then the last two. So these papers, they are like very important papers in the field of artificial intelligence and deep learning. And these papers, they carry lots of citations, some of them going up to 100,000, some 400,000 citations. So that citations is like the number of times the paper has been referenced in academic writing. So these two papers, these ones are highlighted in bolded. They really like highly cited. They are the highest. They carry the highest citation. I think this one 400,000 citation. Then this one about the same thing. Then this one too is about 300 citation. This paper, attention is all you need, is like the paper on that is kind of similar to what really brought about the ChatGPT that we all know. So, and this one, ImageNet classification, I think it's 300 times. That's been cited up to 300,000 times. So it was the paper that really pushed out machine learning, deep learning, that people began to actually see the potential in it. So the assignment is for you to pick one of these papers. So you pick any of these papers you feel you are interested in. Then for the first assignment, because the assignment is divided into like batches. So this first one is just to read the introduction of the paper, the abstract and the introduction. So the assignment is to read, you will still read the other parts, but just as a starting point, you pick any of these papers that of interest to you. You read the abstract, the introduction, then you'd create a video just to summarize what you've learned. So just the abstract and the abstract and the introduction. Then a live video will be submitted that's to summarize what you've read about the paper. So that's what the assignment is all about. So I will put up the assignment on Moodle. So you submit via Moodle, and it's due on Tuesday, October 15. So, like I said, you can pick any of these papers and review. So, is there any question based on the instruction? Yeah? It should be less than, I don't know, it should be less than 2 minutes, or it shouldn't up to 3 minutes. Just something less than 2 minutes. Okay. So I saw a hand at the back. Was the same question? Okay. Okay, so before I continue, is there any question? No. If you are not comfortable showing your face, like I'm not interested in your face, like it's the content of what you are saying I'm interested in. So if you, like for me, if I'm giving these assignments, the way I will do it is that I'll just create like a PowerPoint presentation. Then I will just try to speak to the PowerPoint. Then you can just do the same thing. Maybe a PowerPoint presentation, then is the PowerPoint slide that will be showing. Then your voice would, it's not that you are reading the PowerPoint slide, but you are trying to like articulate what is being shown on the PowerPoint slide. So, or you can even just, you don't really need to do a PowerPoint slide. Maybe you can just the paper itself, you can just share the paper. So since this is just the introduction, so you can just share the paper itself and you can just begin to speak to it. Or another method, maybe if I were you, is maybe the paper has a block diagram. So you can just put up the block diagram and just begin to explain what you understand when you actually read. Because like for me, the diagrams in any paper or in any article is like an indicating factor of, it's just like a summary. Most papers, when they put a system overview or they put a block diagram, that block diagram is like the summary of what they are actually saying. So whichever method you want to use, so you can use it. So before we continue, this researcher, Dr. Fefeli, she was like one of the major researchers in the field of AI, though a paper is not on the list. Like this paper, ImageNet classification with deep neural convolutional network. A paper is not there. But why I didn't include this woman's paper is that the work she did, it was just data. So what she did was she and together with her team, they just collected data, very big amount of data of different objects, different people, animals, places, things, and the paper was just about the data they collected. And it was that data they collected that they used in this number 2 paper to create a deep convolutional neural network. So it was this lady, this doctor over here, that actually created that database of ImageNet. They named it ImageNet. And like I said, this paper here, this number 2 paper, they leveraged on that data set that was created, and they used it to create a deep CNN network. And this is a quote she said. She said in 2012, my ImageNet, that's that database of data of images, combined with AlexNet and GPUs, many people call the birth of modern AI. It was driven by three ingredients: big data, neural networks, and modern GPU computing. And once that moment hits, I think life was never the same for the whole world of AI as well as our world. So she's called the godmother of AI because it was based on her data, like she said, that they now developed complex deep neural networks. And it was that paper, this number 2 paper. I keep mentioning this number 2 paper. It was this number 2 paper that when it's like it, so people now begin to see the potentials in artificial intelligence. So it is similar to what I mentioned in last week. So I asked the question where I said that I asked that when do you feel that AI had been around? So we discovered that AI had been around since the 1950s, but it was just getting to the 90s or the 2000, that's when it became really popular. And the 3 reasons why we gave as it being popular was big data. So back then, there was no data, but now there is data, and it was this woman, Dr. Fefeli, that actually provided the ImageNet. That's important data that actually blew up the field of AI. So she mentioned big data, which we mentioned last week, neural network, that number 2 paper. So as a result of the database, they developed neural network models, and it blew up the field. Then most importantly, modern GPU computing. So as we are going to be seeing, even in this class, the models, the AI models that we are going to be developing, if you run it on a CPU, on a standard CPU, it's going to be very slow because these models are very big, they are heavyweight, and they are very complicated and very deep. So we will leverage the use of modern GPU computing. So who knows the full meaning of GPU? Yeah? Okay. So we are going to leverage the use of GPU in order to run those complicated moments. So these are I just want to re-emphasize the 3 key ingredients of AI. So we'll move on to the business of the day. So I want to start with the Hello World model of AI. So that's what I want to start with. So the purpose of this Hello World model is just to give you the basics of AI. So suppose you have a data set that has the power of a certain car. So the power is rated in terms of the horsepower. And you have the fuel consumption of the car in miles per gallon. So let me show you the data set. Okay, so I think the data set is loading. So you have the power of the car in terms of the horsepower. Then so this is the power rating of the car. Then the fuel consumption of the car in miles per gallon. So we know that the more powerful the car is, then the going to be. So when a car is really very big and it's going to consume more fuel. So that's what I'm talking about. So we have 4 data points. So this is the power of the car, power rating of the car. So this is the miles per gallon of the car. So this car that it has a power rating of 165. So it's very powerful. The fuel consumption is 15 miles per gallon. So it can only go 15 miles, after which the fuel is going to like be diminished. But a car that has less power, 130 horsepower, it can travel for a longer distance with the same amount of fuel. So the aim of this data is to bring out a model from the data set. So you have the data of different ratings, power ratings of a car. You have the data of the miles per gallon. Then we already know the kind of relationship, because we know that the more powerful a car is, the less fuel efficient is it. But we want to put an equation to it. We want to know the model, the mathematical model that governs the relationship between the power of the car and the fuel efficiency of that car. So given this data set, this is the input and this is the output. Because this is the power of the car, then you are kind of measuring the efficiency. So the first step is to plot the input. So to plot the output as a function of the input. So I'm using Excel here. So you're plotting the output as a function of the input. Then I know you all probably in your SS2, SS1, SS3, you people would have done something called linear regression. So a linear regression will fit a line of best fit. So these are the points that have been constructed. Then in linear regression, you fit a line of best fit that would actually give you a model of that scenario you are trying to work on. So if we'll go back to your secondary school, so you have this equation y is equal to mx plus c. So what's this equation? What's it called? The equation of the straight line. So thank you very much. So this x is the input, then this y is the output. So based on this equation, yeah, you are going to find the coefficients. So m and c. So they are the coefficients of the equation. Then you can use using that equation in a certain equation. So I will not. That's not what I'm going to talk about. So you use it to find these coefficients. Then using that equation, you get the model for the line of best fit. So the m and c, they are called the coefficients of the equation. So there is like a function in Excel that can just help you determine the equation of the line. So I just used up I think there's a formula you can use, but I just used up Excel, and Excel produced this equation. So this is like the linear regression model of this particular data set. So all we did was just make a plot, then we just called some Excel function, or you can use the equations if you like. Then it's got the equation model, the model of this particular data set. It gave it to us as this equation. So this equation, it is like I said, probably in your SS1 to 3, you must have done it, and it's called linear regression. This equation is called a linear regression model, and it turns out that in AI, in machine learning, this linear regression model that I've just briefly described, it forms the foundation of an artificial neural network model, so which I'll be discussing later. So the model that we came up with is given by so the model we came up with is given by this equation here. So I already described how I got it. I just used Excel, some Excel functions to get it. But there are some equations that one can use. So this is the equation here. But X is the input, is the power of the car. Then Y is the output, is the miles per gallon. So in place of this, I just put the output and I put the input. So this is now the model. This is linear regression model based on the data set. We came up with a model for that particular scenario we're talking about. So this particular model, we can use it to make prediction. Like for instance, if we know that the power rating of a car is 140, and we want to know the miles per gallon that this particular car that is having a horsepower of 140 can consume, what are we going to do? Exactly. We'll just plug in this 140 into this equation. And once we plug in 140 into this equation, you will just get the answer, which is 0.35 miles per gallon. So this model, like I said, is a linear regression model. It's a linear regression model. And this is the hello world model of AI. So I know some of you are used to coding. So when we say hello world, has anybody written an hello world program before? Yes. So in terms of AI, we call this the hello world model because it's like the simplest model one can think of in AI. So henceforth, we'll start talking about more complicated models. And if you think carefully, you will see that you've done this as far back as in SS1 or so. So this is like the basics of machine learning. So why this is related to machine learning is, if you can remember last week, I was saying software 1.0 and I'll say software 2.0. So I said in software 2.0, you give the data and you give what again? The output. Then it will generate the rules. So this is the same thing we are doing. That data set on Excel, is there. Then that data set, you have the input and the output. So the output is also there. Then from there, we generated the rule. The rule is like a mathematical equation or a model. So this is like the rule. So this is like the very simplest form of machine learning, the most simplest form one can actually think of. So you have the data, you have the output. The rules will be generated at the end. So this is called machine learning. So in the model, in this simplest model, we have some terms that we use, a feature or an attribute of the car. So the feature of the car is also called the attribute of the car, or we can also say that it is the input. So the feature or the attribute is the input. So in this case, the input is the horsepower of the car. So we have a term called the target. So the target is like the output. So in this case, the output, the target is also called the output. So in this case, the output is the miles per gallon. So this is the feature or attribute. This is the target or output. Then what are these values? In normal linear regression, we call them coefficients. So, or parameters, we call them coefficients. But in AI, these two parameters, we call them weights. So they are called weights, since it is multiplying factor of a feature. Okay, so we call this, let me write it clearly, minus 0.086 HP plus 29.075. So this one is called the weight. This also is also called the weight. I will be explaining it later. So these two are called the parameters or the weights of the model. So okay, let me explain why this is also called the weight. So remember I told you that in normal linear regression, you have y is equal to mx plus c. So this is the equation, this is the model we are following. But in AI, it's still the same equation, but it becomes y is equal to w1x plus w0 w1x1 plus w0 x0. So these two equations, y is equal to mx plus c and y is equal to this, they are the same thing. So I will prove to you that they are the same thing. So if n is equal to w1, then c is equal to w0 and x0 is equal to 1. So given this, can you please confirm that this and this are the same thing? If n is equal to w1, c is equal to w0 and x0 is equal to 1, can you confirm that these two equations are the same thing? Okay. So please not able to confirm that. Okay, you are able to confirm that. Okay. So just plug in place of n, put w1. In place of c, put w0. Then in place of x0, put 1. So just do the math. Using this, either this equation or this equation. In place of n, put w1. In place of c, put w0. Then in place of x0, put 1. So once you've done that, so I want you to do it and confirm again that meet me outside the class or meet anybody that is able to get it. So these two equations are the same thing. So we all know this from secondary school, but in AI, this is the notation we use. So these two parameters, so for this model, this simplest hello world model, these parameters, can somebody tell me what W1 is? Given this our simple model, what's W1? Yes, thank you. And what's W0? Yes. So thank you very much. So in this particular model, this is our W1 and this is our W0. So these parameters, they are called the weight, since it's a multiplying factor of a future. So this one, you can say that it's not multiplying everything, but the standard procedure is that it is multiplied by 1, which is W0. So remember here, X0, thank you. So which is X0. So remember I said here, X0 is equal to 1. So the standard procedure is that it is multiplied by 1. So the both of them are called parameters. So please take note of this. These names. So we have our model already. Then, like I said earlier, if you want to estimate an output based on the input, you will just plug in the input and it will generate a prediction. So the model's estimate for the car with a horsepower of 140 is 17.035, and that estimate is called the prediction because it is just a model and the model is not 100% correct. So if for the actual car of the Ford that has an horsepower of 140, if the actual fuel consumption is 17, so you know that the prediction, our model predicted a value of this, but the actual is 17. So the difference between the prediction and the actual value is called an error. So I will still go back to this. I will try to see if I can go back to this later, because this is really very important in AI, and like I said, it's like the hello world model of AI. So if you are really able to understand this hello world model, then I think we should be good from here. So, but if you are not able to understand what I've just said, probably you can just come to my office after the class, then I would explain this to you, because if you don't understand this, which is the hello world model, then we are going to more complicated things henceforth. So I will try to come back to this later, but I want you to know that you really have to understand what I've just said, because it's the background in which you'll be working on. So before we actually make some progress, I just need to give you the definition, some terms in AI and their definition. So in AI, we have something called data sets. So data set is just a collection of data that you have or that you are using. Because like I said in the last week when we started the class, I said that the foundation, the bedrock of AI is data. So there has to be data. So we talk about the data set of images. The data set that is made up of images, like, you know, when I was talking about Dr. Fefeli, that her own contribution, her own major contribution in the field of artificial intelligence. Can somebody remind me what I said she did? So what's the name of that data set? Images. So thank you very much. So her contribution was that she created a data set of images that can be used from AI. That was our own contribution. So the background of AI is data. So a data set can be made up of images. It's not only image. A data set can be made up of, it can be in spreadsheet form, like that spreadsheet I showed earlier. So it can be videos, it can be it's just data. So when you have a database of images, you know there are lots of images, maybe 100,000 images. Each image can be a data point. So you can say that one image is a data point. You can also say that one image is a sample, or one image is an instance. So these are the terms we use in machine learning. Instead of just saying that one image in the data set, we can just say the data point. We can call it sample. We can call it instance. So these are just to introduce you to the terms that we use in AI. So we talk about tabular data. So it's not only image that is like the data that you can use for AI. You can use tabular data like spreadsheet data. So in terms of tabular data, we'll say that a role is a data point. A role. So for instance, you have a tabular data now that consists of the input then the output. So we say that a role in this data set of numbers is a data point. So we can say it's a data point, and each individual column. So a row is a data point, but each value in each column of that row, you can call it an attribute, a feature, or a dimension. So we are dealing with tabular data now. So a row is considered as a data point. Then each column in that particular row can be called a feature, an attribute, or a dimension. So we want to talk about, so you can either call it these three names, which they mean the same thing, but there is a slight difference between an attribute and a feature. So an attribute, they're basically almost the same thing, but there is a slight difference. So an attribute can represent the characteristic or property that is observed or measured. So what you are directly measuring, you can call it the attribute. Like for the Eloquent model, what you are measuring is the fuel consumption in miles per gallon. So you can call it the attribute. So other attributes can be color, size, weight, etc. Then feature may be used to represent something broader or something transformed, a transformed attribute or abstract values. So let me explain this. For instance, now, if the AI model you are trying to come up with is, you are trying to recognize the different you are trying to recognize language. So for instance, in the last set, I gave them one of the projects I gave was they should develop an AI model that can distinguish between different meetings. So in different languages, like maybe in English, it's hello if you want to greet, or good morning. In Yoruba, it's a carol, then Kwana in Igbo is they have their greeting. So they collected data of different people greeting in different languages. So this is Yoruba, this is English, this is Hausa, this is Igbo. So the task was to develop an AI model that could distinguish between these four languages. So the data, the raw data is sound. You know when you are talking, it's like is a sound, and the sound is like in MP3 format. Now it turns out that data of the sound is the attributes. So it represents what is directly observed or what you are actually measuring. But it turns out that it is not actually that sound that you are going to feed directly into the AI model. There are some transformations that was done on that particular sound, on that particular input. So it's after one transformation that was done was Fourier transform. Like they converted the sound, not the sound is in the time domain, they transformed it into the frequency domain. So after doing a transform of the input, we will no longer call it attributes, we will call it future. So attributes and future, they are the same thing, but future is a little bit more advanced. Is when you get the input, if you do some transformation to the input before you feed it to the AI model, then you are no longer calling it attributes. You will now begin to call it futures. So futures are intermediate values produced by the model or algorithm. So the transformation you do before it actually gets to be fed to the AI model. So we'll now talk about dimension. So we said attributes, future, and dimension, they're basically the same thing. But in dimension, the more generic term is like the value that is in a column. Remember I said that the whole row is data points, then each of the values is a column. So that means that if the data point has 10 values, then it means it has 10 dimensions. If that particular data point has six values, then it has 6 dimensions. So that's what we are talking with in terms of tabular data. So the dimension may mean the attribute, the feature, or the column which are said, and it can also mean the number of levels in a nested array. So dimension can mean 2 things: either the value in a column or the number of levels in a nested array. So I think this one you'll be more familiar with it, because if you have a data that is given by this, we said that this one has 2 dimensions. So the number of rows and the number of columns. So we said that this particular data set has 2 dimensions. So for instance, an image. Now, an image can have 2 dimensions: the height and the weight. So dimension can mean different things. So in terms of an image, we have seen that an image is considered to have 2 dimensions. So the row multiplied by the column. So the dimension can be 3. So if the dimension is 3, in AI, colored images, we say that colored images have 3 dimensions. So can somebody tell me why a simple image, a black and white image, we say it has 2 dimensions? So the row multiplied by the column. So can somebody try to give me an explanation of why a colored image is 3D? So a black and white image is 2D. So why is a, yes?
Because the color will be a combination of red, green,
Good. So thank you.
and
Okay. So he gave the correct explanation. For a simple black and white image, an image is made up of pixel values. Then each, for instance, you can say that this image is 228 by 228. So if it's a black and white image, the pixel values can be from 0 to 255. So each pixel value in this image, it will just range from, the values will range from 0 to 255. But in a colored image, the pixel value are a combination of 3 components, like you rightly said. So it's a combination of the green components, the red component, and the blue component. So given this, so when you look at a simple image, an image that is colored, is actually a combination of 3 colors, RGB. So we say that though it is 2 by 2, the third dimension is due to the color. So making colored images 3-dimensional. So the height, the width, and the channel. The channel represents the color components, the RGB color components in that particular image. So we now go to, we've talked about 3D, that a colored image is 3D. So we also have 4-dimension, we also have the 4D. So if you have a combination of colored images, you have, like, this is a colored image, this is a colored image. I know, and we've already clarified that one colored image is in 3D and another colored image is also in 3D. So if you have those combinations of 3D image that is stacked up, then we say that it is now in 4D. So it is now in 4D. So the 4 components are the image ID, the channel, the height, and the width. So these are the 4 dimensions we have. So we've looked at 1 dimension. So for 1 dimension, we just talk about particular data sets in which you have a table. Then the number of columns in that data point represents dimension. Then for images, you can have 2 dimensions. That's the height and the width. For 3D, it's a colored image. The color component has introduced the 3rd dimension. Then you have the 4D, in which the image ID is like the 4th dimension. Can somebody give me an example? There's an example of 4D, of a 4-dimensional data. Based on this explanation that wasn't stated, like I think it was not written there, but you can apply it from the explanation. So the explanation is that if you have colored images, multiple images stacked on top of each other, then we say that it's 4-dimensional. Can somebody give me an example? Yeah. No, it's a question. Yes, that's what I'm saying. So I'm not asking a question that, can somebody give me an example? How can you stack exactly video? So a video is 4 dimension at a certain amount of frame rate. So a classic example of 4D is a video. So videos are just images that are stacked on each other at different points in time. So as it is stated here, it is quite unlikely that you will ever see 5 dimensions when dealing with typical tags. So the worst you can get to is 4D. So if anybody knows of a 5 dimension, so you can let me know after the class. So, okay, yes? Okay. Yeah, so he asked a very, very good question. The question is really very good. So his question was that if it's black and white image, and the black and white image is like stacked on top of each other, will you classify that black and white video? Is it 3D or is it 4D? So the answer to your question is that it is actually, we'll classify it as 4D. And the reason why we'll classify it as 4D is because when we are doing, we'll still get to CNN, convolutional neural network. When we are doing convolutional neural network, if your input is black and white, there will be a transformation that will transform that black and white into RGB. So CNN, convolutional neural network, do not normally work with black and white images. So if you have a data set and the data set is just black and white image, the AI model, which is CNN, which we will talk about later, will transform that black and white, will transform it into color. So in AI, in deep learning, the images we work with they are 3D images. They should have color. So when we get to CNN, you will see, yes, CNN, convolutional neural network. So when we get there, you can ask your question again, then I will explain that transformation to you. So like I said, we will consider that is 4D because in the intermediary stage, there is a conversion from 2D, which is black and white, to 3D, which is colored. So we are still going to call it 4D. Then we now talk about, so what I've just been saying previously, when I was talking about dimensions, attributes, features, data points, I've just been referring to the input. There is the output also, because remember in software 2.0, in machine learning, you will give it the inputs and you give it the output, then it will produce the code, which is the model. So we have not mentioned the output so far. So this is the output. The output is also like the answer. So in machine learning, instead of calling it output or answer, you can call it a label or a target. So what I've just been saying previously is just inputs. Inputs are the attributes, features, or dimensions. Then the outputs are also the target of the label. So we already know what input is and what output is. But I'm just trying to introduce you to some machine learning terms. So in place of output, we call it a target or a label. So if in the lecture notes you are seeing a target or a label, it's just, I'm just telling you this so that you will understand what is being said. So the output is like the answer. So for instance, if the input is like the images of different animals, then the label is just the answer. What is the name? of it. It's referred to as the target. So the name can be, it can be like a specific alphabet or set of alphabets, or it can be numerical. So the term target may refer to more complex answers such as a combination of numeric values and names. So all we are saying is that the target, the output, it can be numeric values, it can be names, or it can be combination of both. So if it's for tables, the target is always numeric, and is always the last in the column. So, and like I said, it is different from the input. So the input, I said, is attributes of features. You can call it attributes of features. Then the target or label is the output. So you shouldn't mistake the output with the features or the attributes. So we'll now talk about artificial neural network. So because we tried to, that Hello World model I tried to introduce to you, it's the simplest form of artificial neural network. So we'll now talk about ANN. Like when last week I said that artificial intelligence is trying to give machines cognitive functions, giving machine cognitive abilities like problem solving and reasoning. And also last week I mentioned that in software 2.0 you have the inputs, which are the attributes of the features, and you have the answers, which are the targets or the label, and it's going to generate the rules. So, and I said that model that we presented is like the same thing. It's like the same model we human beings we use when we are learning. So the data is shown to us, and the answer, we are also giving the answer. Then back in our brain, there's some kind of network that will generate the rules that will make us to remember, such that when we encounter something similar, we can infer from it. So that was what I said last week. So, and that is the way we human beings, that's how we reason. So it's the ANN is similar in the sense that in our brains there are neurons. There is a network of neurons in our brains that make us to be able to generate the rules, the models based on just the targets, the answers, and the data. So our brain uses neural network to do lots of high cognitive tasks. So in the same vein with our brain function, the ANN was developed, and it was inspired from the understanding of the nervous system, our own nervous system. So, and the way our nervous system work is that this is like a diagram of just one of the neural network that is in our brain. So we have something called the soma. The soma is the cell body. We have the dendrites. The dendrites is like an input, because in our brains, when information is transferred from one neuron to the other. So let's say this is one neuron. This is a neuron. So we are now talking about our brain now, because we are trying to I'm trying to make a case of AMN being similar to how our brain is structured. So in our brain, the nervous system of our brain, we have I don't know, maybe billions of trillions of neurons in our brain that are connected together for processing of information. So we have trillions of these neurons, or trillions multiplied by trillions of these neurons in our brain. So this is just a simple one of those trillions we have in our brain. So in our brain, you have this is a neuron. So we have the soma. The soma is the cell body. Then we have the dendrite, is the input, because one neuron is always connected to the other. So it is the dendrite is like the mechanism for connecting one neuron to the other. So this is the dendrite, this is the soma, this is the axon. This is like the it connects you connect from one neuron to the other using the dendrite. Then the axon is just like the output, because the neurons in our brain is just like a model. We can call this like a model. So remember that we are dealing with the human brain now. So you have the input. This is what is coming into the cell body. So this is the input. So it turns out that this soma, I try to call it the model, and what is coming in is different from what is going out, because once there is an input, there will be some kind of processing. There will be some kind of processing here. Then based on that processing, there will be some output. So the input that is coming in, it is not the same thing that is going out as a result of this processing that is done in this place. So this is the input, then some processing is done, this is the output. Then you have the dendrites that will connect to another neuron in our brain. So remember I said that there are trillions and trillions of these neurons in our brain. That's what our brain is made up of. So it turns out that the basics of AI is actually the ANN, the artificial neural network. So we are trying to, remember as in AI, you are trying to give machines the cognitive function of a normal person. So a kind of something similar to was developed based on that, and which is called the artificial neural network. So this one is the original neural network we have in our brain. But in the case of ANN, we call it artificial neural network. So I will give the relationship between the biological neural network and the artificial neural network. So remember I said the dendrites. What did I call the dendrites? The inputs. Yes. So similar to the dendrites, the artificial neural network, in place of the dendrites, you have input signals. So this is our biological neural network, just one. And this is the structure of the artificial neural network. So you have instead of the dendrites, in an ANN, you have the input signals. So this soma is the cell body, and that cell body is the model, and it is called the neuron itself. So instead of the soma that is in our brain, we use the cell body, which are the neurons. So the soma is the neuron. Then this axon is the output. I called it the output. Then in an ANN is also called the output, but in our brain, we call it the axon. Then there's something I didn't mention. There was something I didn't mention here, the synapse. The synapse. So the synapse is what actually contributes to the model, because I called this the model. So in our brain we call something the synapse, but in ANN we call it the weights. You know, I mentioned weights earlier. Yes, I mentioned weights earlier. So when I said that y is equal to W1 x1 plus W0 x0, so I call this the weights. So in an ANN, which is the information processing model we are trying to look at, the weights is called the synapse. And why is it called the synapse? You know, you have the inputs. These dendrites, they are the inputs. So the inputs, let's say x1 and x0. So x0 and x1 represent the inputs. So in machine learning, instead of saying the inputs, what are the names you call it? Features, attributes. Okay, so these are the inputs. Then you have the inputs, then you have the output. So this is the output. So what other name for the output? Okay, so these are the inputs and these are the outputs. So remember I said that the input is not the same thing with the output. So there's a kind of model, some kind of transformation within the cell body that does some transformation such that it produces an output. And it is the synaptic gap in our brain, or the synapses in our brain, that contributes to a function that produces the output. But in terms of the ALM model, we have the weights. So if you look at this equation here, which is like the LO1 model of ALM, this x1 and x0, they are the inputs, then y is the output. So this y is equal to, so I'm going to write out an equation on the board. I'm going to write out an equation on the board. Then I will go around and you will convince me that the equation I've written is the same thing as this. So in your notes. So let me write down the equation now. So the equation is y is equal to this equation. I'm writing this equation. So in your notes, convince me, prove to me that this equation is the same thing as this equation. So I will go around now. able to prove that this and this are the same thing. So why did I bring out this equation? Remember, I'm trying to talk about the weight. So it turns out that this one is the weight, while this is the input. So this equation can also be written as y is equal to wx. So if this is equal to capital letter W, and if this is equal to x, then y is equal to wx. Do everybody understand that you can simplify this to this? So if you don't understand, just this one is w, then this one is x, and you can simplify it like that. I remember this y is the output and x is the input. So it turns out that in our brain, the dendrites, what is coming into the dendrites, input is coming out. Then in the output, y is coming out at the output. Then this model is just given by y is equal to wx. So the weight would act as a form of transformation that will transform the input into the output. And in our brain, it is called the synapse. This W is called the synapse, but in ANN it's called the weight. So it turns out that, remember the equation we stated is mx plus c. So it turns out that in AI, we just say y is equal to wx. And the reason this and this are just the same thing, and the reason why they are the same is that this w is equal to this, and this x is equal to this. If you expand this out, you will get this. Then if x naught is equal to 1, you will eventually get y is equal to mx plus c. So this is the biological neuron, the brain, but this is the ANN, the model that we are working with. So in place of the soma, you have the neuron. In place of the dendrite, what it includes, the axon is the output, and the synapse is the weight. So it's the weight I've just tried to explain. So it turns out that, like I said, in our brain, we have millions, trillions, billions of this network, of this neural net, of this network in our brain. But in ANN, these are the neurons. So these are the neurons. Then it's not just only one level, because if we say that y is equal to wx. So let me use a simpler scenario. So for instance, you have this scenario now. So these are the inputs. These are the inputs. So let's say this is x1, x2, x3, x4, x5, x6. Then this is the output, y. So it turns out that the weights are w1, w2, w3, w4, w5, and w6, such that y is equal to w1x1 plus w2x2 plus w3x3 plus w4x4 plus w5x5 plus w6x6. So this is the model. So this is the simplest ANN you have. So these are the attributes. These are the features. Then there should be some weights such that when you multiply the inputs by the weight, you will get the output. Then this equation y is the same thing as W1x1. So it's the same thing as this y is the same thing as W1, W2, W3, W4, W5, W6 multiplied by x1, x2, x3, x4, x5, x6. Do I need to convince you that this and this are the same thing? Okay, we already know that this and this are the same thing. So in this case, this one is called W and this one is called X. So a simpler model is Y is equal to WX. So this is like the simplest neural network model. So these are the weights or the coefficients or the parameters. Then you have the inputs. So these are the inputs. So these are the neurons. Then these are the inputs, which in the biological case are the dendrites. Then these are the weights, which are the synapse. Then this is the output. So it is the weight that kind of does the transformation. So this is like the simplest neural network. So let's go to this. So this is a lot more complicated. In the case of the previous example, that was like the simplest case. But it turns out that, in our brains, there are billions of these neurons. And it turns out that in between the input and the output is not just one level of synapse, one level of weights that will do the processing. There are multiple levels in between. So this is what I'm talking about. So these are the inputs, right? So in an artificial neural network, you can have, this is called the inputs layer. So I'm introducing a new term now called layer now. No, previously I just called this input, but now I'm calling it an inputs layer. Then this is the output layer. Previously, in that previous example I did, let me show you. In this example, there was nothing in between the input and the output. There was nothing. This is the input layer, this is the output layer. There was nothing in between the input and output. But it turns out that for deep learning, for deep neural network, there are intermediate layers in between the input and the output layer. In this case, we have one layer that is in between the input and the output. So it can be one layer, it can be two layers, it can be three layers, it can be four layers. Like for instance, in this example, how many layers do we have in between the input and the output? 4. 1, 2, 3, 4. You have 4 layers in between the input and the output. So for deep neural network, there are layers, multiple layers in between the input and the output. Remember the example, the hello world model I showed you, which was y is equal to W0 x0 plus W1 x1. So that was like the simplest you can get. I call it the hello world model because for deep learning, there has to be some layers in between the inputs and the outputs, cannot just be one. So let's go back to this case. So for this case, these are the inputs. Let's call it x1, x2, x3, x4, x5, and x6. Okay, just to make things, let me just open a new line. So you have 1, 2, 3, 4, 5, 6. So white. So these are the inputs. Then, just to make things simple, and let's say this is the output. So now I'm going to put a layer. This is the input layer, this is the output layer. So before, we're just connecting the inputs directly to the outputs. We're just connecting it directly to the output. And that was like a hello world model. But really, in deep learning, there has to be some neurons in between. So this is X1, X2, X3, X4, X5, X6. So W1, W2, W3, W4, W5, and W6. And this is Y. So you can write the equation. So Y is equal to Wx. So we've already proved that. So let me go to the case where you have something in between. So 1, 2, 3, 4, 5, 6. Then this is the output. This is the input, this is the output. So now we have another layer in between. So please just watch carefully. So you have this. So remember, this is X1, X2, X3, X4, X5, and X6. So these inputs, they go into one of the neurons in the hidden layer. Then the second neuron in this hidden layer, some inputs go into it, then finally it goes into the output. So this one, we call it W1, W2, W3, W4, W5, W6. But given that there is another neuron again with different weights, so what we are now going to do is that we'll call this W11, W12, W13, W14, W15, W16. Then the synapse, the weights that are entering into this one, we call it W21, W22, W23, W24, W25, W26. So in the case of that simplest one, since it's just one, we'll just call it W1, W3. But now, since there are two, different weight has to enter the second neuron. So maybe we'll call this one, the last one, let's say W1 and W2. So in this case, you have two neurons. You know, this is the input and this is the output. So you have two neurons that are, and then this is we call the layer in between the inputs and the output layer, we call it the hidden layer, the ANN. So this is the input layer, this is the hidden layer, and this is the output layer. So in this case, we only have one hidden layer, but that hidden layer has two neurons. So if you wanted to describe this artificial neural network, we said that this artificial neural network, please listen to me carefully. This artificial neural network, it has one input layer, it has one output layer, and it has one hidden layer. There are 6 neurons in the input layer. There are 2 neurons in the hidden layer, and there is 1 neuron in the output layer. So that's how we describe this. Then if we want to represent it in terms of mathematical equation, so let me call this one y11, and let me call this one y12. So y11, can you write the equation for y11 for me? Can you write it for me? So I will go around. What is the equation for y? Let me give you an hint. Y11 is equal to W11 x1 plus W12 x2. So complete it. I will go around. Then write the equation for y12 for me. So I want you to complete it. After writing the equation, then you will now write it in form of matrix form. So okay, so you write it in matrix form, Wx. So after writing y1 and y12, then this is y. Write the equation of y for me too. You write y11, y12, then you write y for me. So I was able to go around. So from what I noticed, the topmost mistake people were making is that why so the topmost mistake people were making is the notation. So y is equal to wx. It's not y. So it's always y is equal to wx. So this part has to be w and this part has to be x. So you will take note when writing. So this part has to be w and this part has to be x. So if you look at this neural network, it has one question that one person asked me, which was a very good question, is that you can only have one input layer. In an ANN, you can only have one input layer. And you can only have one output layer. One output layer. So it has to be just one input layer and one output layer. Then in between, you can have multiple hidden layers in between the input and the output. So the input is always one input layer. Then the output is always one input layer. You cannot have two input layers. Then you can have multiple hidden layers. So if you want to describe this neural network, it has one input layer. It has 6 neurons in the input layer. It has one output layer with one neuron in the output layer. It has one hidden layer with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, with 10 neurons in the hidden layer. So that is the way we represent it. So if I were to tell you, to give me the equations for this, from this y11 to y 110, I think you should be able to give me the equation, right? Then you should be able to give me the equation to the final output layer. Then, before we leave this place, before we leave this ANN, I want somebody, please keep quiet everybody. So I want somebody to look at this ANN. If I were to tell you to describe this neural network, can somebody stand up and describe it for me? Yes.
Have one input layer with 5 neurons. Then it has one output layer with 4 neurons. Then it has 4 hidden layers with each of them having 5 neurons.
Yes. So thank you very much. So that is the way to describe it. So which is really very, very perfect. Okay, yes. So thank you very much. 1, 2, 3, 4, 5, 6, 7, yes. So it has 7 neurons in each hidden layer. So before we go on, I want to just give a brief comment on the difference between our brain, our own biological brain and ANN. So in this ANN, we are trying to create a model similar to the way information is being passed or is being processed in our brain, and that was what brought about this ANN. There are differences. So in our brain, like I said, we have trillions upon trillions of neurons, but in an ANN or in deep learning, we also have a number of these neurons also, and we also have a number of layers, but it cannot be as much as the one in our brain. So even the GPT models, it has millions of parameters of weights, but you cannot compare it to the one in our brain. The one in our brain is like a trillion times more than any model that anybody can come up with. That's one. And number two, which made me say it because of the question that one person asked me. For a deep architecture, like I said earlier, you cannot have one input and one output. But for our brain has multiple input layers and it has multiple output layers. But for a deep ANN or a deep architecture, it is just only one input layer and one output layer. Our brain has millions of input layers and millions of output layers. Can somebody tell me why our brain is able to handle millions of input layers? And another person should tell me why a deep learning architecture or an ANN can only handle just one input and one output layer. Anybody that knows? So she gave me the perfect answer. She said we have different multiple sensors. And okay, let me expand on what she said.
The cost rep, is it 500 level?
Yes.
Cost rep.
Cost rate.
Sorry.
Okay. So to add to what she said, the reason why is because we human beings, we can do multiple things. We can do multiple things at the same time. So like I am right now, I'm talking, right? And at the same time, I can walk, and at the same time, I can hear. At the same time, I can experience different things and do different things at the same time. Even the way I'm talking, I'm even still thinking about some other things. Like, though I'm teaching you, but I'm still aware of other things I need to do when I give this class. So we can multitask and we can do several things at the same time. But ANN, it's just good at just one task. Like for instance, ChatGPT. In the first class, I said ChatGPT is just limited. You can give it questions, then it will produce answers for you. Probably it can generate images. It can, I don't know, it can do some other things, but there are some things it cannot do. It's not like a human being. You cannot now say that it's now a human being. Because though it looks as if it can reason, it can think, but can it speak? Though there are some Gemini, who have used Gemini before. Gemini can convert the text to to speech. So it can talk, but then can it walk? But then can it, does it, I don't know, you cannot say that it is a human being. You cannot compare it to a human being that can do multiple things at the same time. So these deep learning models, they are just for one task only. So they just have one input. And it's just one output that's giving this input produce this output. So it's just for just one specialized task. So we human beings, we are different in the sense that we can multitask and we can do multiple things at the same time. So that's why we have millions of input layers in our brain. We have millions of output layers. For a deep architecture, it's just as one input layer and one output layer. So that's why you have it. Though for the large language models, they have billions of parameters, so billions of weights that it's being used to produce the final output. But even the millions and billions of parameters that these GPT models have, you cannot compare it to our brains that have millions and trillions of these parameters, which act as synapse. So we've been able to talk about ANN. So we'll now go to the setup and environment. So we are going to, so it turns out that these deep learning models, before I actually leave, I didn't actually explain. So we have the shadow architecture and the deep architecture, or we call it the deep learning model. For the shallow architecture, it just has like one hidden layer in between the input and the output. But the deep learning architecture, please keep quiet. The deep learning architecture has many hidden layers in between the inputs and the output. So we call it deep because it has much layers in between the inputs and the outputs. And as a result of it having more number of hidden layers, the weights are also more. Like for instance now, can somebody tell me for this particular deep architecture, can somebody just do a calculation for me of the weights, the number of the weights of this architecture, the number of parameters. Parameters are also called weights. Can somebody just do the calculation for me? Or can somebody come forward to do the calculation for me? So here, 1, 2, 3, 4, 5. That's five weights. So each of these 5 will go into 7. So 5 times 7, 35. So for this part, you have 35 parameters. Between here and here, how many parameters do you have? 49 parameters. Between here and here, how many parameters? 49. Between here and here. So here, 28. So when you do the calculation, how many parameters? 210. So it has 210 parameters. So this architecture is that we call it deep architecture, deep learning model. It does has 210 parameters, where our brain has trillions, billions, multiplied by trillions and billions of parameters. So even the GPT models that ChatGPT models too, it has some number of parameters, but you cannot compare it to the number of parameters we have in our brain, and that is what makes us human beings. So like I said in the first class, we have the weak AI and we have the strong AI. So the weak AI is just good at one specialized task, but the strong AI can do everything. that a human being can do. So at the moment, we said that there's really no strong AI yet. So we now go to the setup and environment. So, like I've said, deep learning models, they are very computational expensive. They are very, because of the number of parameters, they take a lot of CPU power. So in terms of computation, so it is possible to use the normal CPU to run smaller models that have just small parameters or small weights, but it is better to use a GPU. So, do anybody have a GPU this time? And if somebody should have, you have a computer that wants a GPU. Which person? Okay. Okay. So, did anybody have a GPU? Are you raising up your hand? Okay. So, and unfortunately for us, we want to be able to run these deep learning models. So what we are going to do is that we are going to make use of free cloud providers like Google Colab, Cargo Notebook, or Amazon SageMaker Studio. So these cloud providers, they they have a GPU, they have their own GPU which you can access from the cloud, which you can use. So I will try to see so we are going to be making use of Google Colab in this class. Who has used Google Colab? Who has an idea of Google Colab? Okay, so thank you very much. So to use Google Colab, it is straightforward. You will just go to Colab Google. So if you have a Gmail account, then you are good to go. So it's just collab.google. So this is how it is. So like I said, once you have a Gmail account, then you will have access to Google Colab. So as I'm using here, Colab is a hosted digital model service that requires no setup to use and provides free access to computing resources, including scheduling GPUs and TPUs. Colab is especially well suited to machine learning, data science, and education. So we want to be able to make use of. The only reason why we are using Google Colab is want to have access to the GPU that's the Google Colab, so that because we are going to run deep learning models, and the deep learning models they are computationally intensive, very computationally intensive. So we cannot and I don't know if anybody has a GPU in this class that is not talking, but so since for me I don't have a GPU, right? You have a GPU. Oh wow, that's good. So probably you don't need to use Google Colab. You'll be able to run your own model straight from your GPU. So when you first of all open Google Colab, this is what is going to give you. You say open Colab, So that's why the files came up. But if you are new to it, it will take you to this welcome to Colab. So you can read it. But if you want to create a new notebook, you just click on this new notebook. And you already have access to it. So, like I said, we are going to be using Python programming. So Python, so it's very adaptable with Python. Google Colab, it's Python and R. So I'm talking about the GPU. So normally, Google Colab will use the normal CPU. Please keep quiet, everybody. It will use the normal CPU. So if you want to change it to use a GPU, you will go to runtime. Then you will say change runtime type. So once you click on change runtime type, it will now indicate the hardware accelerator to use. So by default, it's using a CPU. So you have to change to a GPU. So if you want to use the GPU, then you will now click on this. Then it will now change to the GPU. But I want you to note that the GPU they monitor the usage. So if you are using the free version, probably it has a number of limits. So the first models will be running. They don't require GPU. They are simple models. We are going to do the one of linear regression. So it's a very simple model. You don't need GPU. Because if you start to use the GPU, now for simple models that are very straightforward and you can use the CPU, you might exhaust your limits, your free limits. And the time where we really need it in the course, you will not be able to use it. So we'll leave it at CPU for now. So when we really get deep into the course, then you can, and the models are very big and computationally intensive, you can now change it to GPU. Let me give an example. Like one of my project students, last time he was working on a project, and to actually build the model, the AI model, it would take, I don't know how many hours he said. He said maybe like 48 hours just to build the model on a CPU. So it would take, like you would just leave your computer on for 48 hours to build the model. So, but if you use the GPU, 1 hour, you are done. So it's so that's how you can use it. But let's leave it as a CPU for now, because we are not doing something very extraordinary as a starting point. So I'll just close it. So apart from Google Colab, there are other platforms that you can leverage on to run deep learning models, like Kaggle Notebook. And everybody use Kaggle Notebook before to run models. Okay, there's also Amazon SageMaker Studio that you can use. So we are going to be using Google Colab, but if you are used to using Kaggle Notebook, and that's fine, you can use it too.